Hello, I am Luca Saiu and I will present a type system for weighted automata and rational expressions. This is a joint work with Akin Demay, Alexandra Druid-Lutz, Sylvain Lombardi and Jacques Zakarovich. Our software Vaucanson is a general purpose platform for weighted automata and transducers. It is generic, by which we mean that it is very widely applicable. It supports acceptors in the traditional sense, both weighted or not, and transducers. It supports not only automata but also rational expressions, and it supports a wide different range of weights, such as booleans for acceptors, the usual numeric types, and more funky stuff such as tropical algebras. Labels can be single letters, words, possibly the empty word, and so on. By letter we mean either small characters, such as the C++ char type, or wider types, which can be useful for Asian languages, for example. Performance is a critical concern for us, so Vaucanson is written in C++ as a fully templated library. It does not employ dynamic polymorphism, and we prevent ourselves from using the virtual keyword for dynamic method dispatch, which is potentially inefficient. So we use templates instead of that. We have very efficient algorithms and data structures, which is potentially in conflict with our third goal of flexibility. In order to be friendlier to users, and particularly to beginners and students, we implement a further layer on top of the C++ layer, still in C++, coupling each object with its type. So each object carries its own type as part of the value in a dynamically typed system, and this frees the user from being concerned with template parameters which are very inconvenient to handle. On top of this dynamic layer, we have a further layer written in Python, which is graphical and interactive and very friendly to experiment. And this is written in Python and over a web interface based on IPython notebook. You're gonna see a demo later. Even before starting to speak about types, let's speak about automata in general. And even before speaking of weighted automata, it is convenient to go back to unweighted automata and speak about computations and how they generalize to the weighted case. How do we recognize the string BB on this automaton? Well, we have two paths. The first one remaining in the first state when recognizing the first letter B, and then going to the second state and then accepting. So in a sense we can say that we compose the true value and the true value with an AND, because we need to recognize a letter at each transition. This is not the only accepting path we have for this automaton. We also have the second accepting computation in red, by which we first go to the second state, recognizing the first B, and then stay on the second state, recognizing the second B, and then we end. So we have two different ways to recognize T and T, essentially, to compute T and T. How do we combine these two T results? Well, we do combine them by an OR operator, because either would suffice in this case. And so we can say that this automaton, given the string BB, returns true. How can we generalize this to the weighted case? Well, we take a similar automaton which has weights associated to labels. When a weight is not explicitly indicated, such as here, for example, it is considered to be 1, where 1 is the multiplicative unit for the appropriate set of weights, which is the integer set here. And we can see that there is an explicit 2 over a few labels. Let's recognize BB, and there is the first path, still the same, recognizing first the weight 1, then recognizing a label B with associated the weight 1, then a second label B with associated the weight 1. We generalize the previous AND into a multiplication, so we have 1 times 1 giving 1. We also have the second accepting path, which is this in red, where the first label we traverse as weight 1 and the second as weight 2. By multiplying that we get 2, and by summing those two we get 3. So you can see that the OR operator of the previous case has been generalizing into a plus operator of the set of weights. So we can see that this weighted automaton given bb returns 3. We have different kind of weights. We have the Boolean case for unweighted recognizers, which you just saw. We have the integer case with the usual sum and multiplication that you saw as well, and of course we have other similar cases such as the rationals and reals. We can go a little more exotic and use the minimum operation as a sum and the plus operator as a product. This works. It can be proved that this is still a semi-ring, and it is useful. With some care, we can use rational expressions as well as weights, even if this raises some concerns, so we have to be careful. In general, what we require of weights is simply to be a semi-ring, and rational expressions are not technically a semi-ring over weights, but they can be used with some care. Given two weights, they can be combined into a tuple of weights, and this is still a semi-ring, and so on. What can we accept as labels? Well, letters are possible labels, of course. Nullables are just letters or the empty word. Words are just sequences of letters of any size, including 0. If we have some sets of labels, we can combine them into tuples, and tuples still yields valid labels. This is very useful to encode transducers, because you can have different tapes as different elements of tuples. Of label sets, we just require them to form a monoid, so it is very easy to make a label set. What is a context? A context encodes the type of an automaton. It can be defined mathematically as a pair, a label set and a weight set. Notationally, it is convenient to represent it with an arrow, because this reminds the user that we are more or less speaking about the type of a transition, consuming a label and producing a weight as its associated output, so to speak. So, for example, in a traditional non-weighted recognizer here, we can accept a letter of the set AB and produce a Boolean B as a result. On the right-hand column, you have rational expressions of the same type, not necessarily associated with the same language, of course. So here you can see that we can recognize a nullable set, including the empty word, and give out an integer number as a weight, as an associated weight. Of course, initial weights are also acceptable. Going a little more complicated, we can have a weight which is a letter and a word. Okay, so this is a couple, and the associated weight in this case is a rational number. Even more complicated, we can have a traditional letter, and as a weight we can have a rational expression which internally contains another context, of course. So what is this rational expression made of? It is made of letters which are labels which are letters of the set x and y, and weights which are rational. Okay. How do we compute over types? We use the usual notation for subtyping. We write that A is a subtype of B if all the values of type A are also values of type B, and this is in a set theoretic interpretation more or less means that A is a subset of B. It is quite easy to imagine a reasonable subtype notion for label sets. A singleton set containing only the empty word will be a subtype of any nullable set for any alphabet. Any alphabet will be a subtype of a nullable set with the same alphabet, and a nullable set for some alphabet will be a subtype of the word set for the same alphabet, which is intuitive. Now let A and B be alphabets, such as A is included in B. Then we have that A is a subtype of B by definition, and the subtype relation extends in a very natural way through nullable sets and word sets. Okay. In the same way, we have a subtype relation over weight sets. For example, it is intuitive to see that Booleans with and or are a subtype of naturals with plus and times, which is a subtype of integers, which is a subtype of rationals, which is a subtype of reals, and so on. We could have complex here with didn't implement them, but it is trivial to add if needed. And as a separate branch of the graph, we have booleans, which are a subtype of z-min, where z-min is a tropical algebra with min and plus. It is also convenient to make labels comparable with rational expressions and weights comparable with rational expressions. This will make us will permit us to introduce injections operators easily as you're going to see in a minute. How do you define a subtype relation over context expressions in Automata? It is actually very natural and very easy. You can see that relations is the subtype relation is covariant, and in particular, if L1 is a label set which is a subtype of L2, and the weight set W1 is a subtype of W2, you see that the context L1 W1 is a subtype of L2 W2. This extends in a completely natural way to rational expressions and automata over the same context. We have a subtype relation over label sets, which is again pretty intuitive. For example, here you can see that the intersection of A and B, where A and B are alphabets, is a subtype of B, which in its turn is a subtype of nullable B. Okay? Given the subtype relation, it becomes easy to define in a standard way the join and meet operators, where join is the least upper bound between any two values, v1 and v2, and meet is the greatest lower bound between any two values, v1 and v2. When we say value, of course, we mean either a label or a weight set. We are using the same notation for both. Let's give an example. What is the join of Q and this radix type? Well, you can see from the previous rules that it is still radix, where the associated internal weight is the join of B and Q, which is Q. What is the meet of two alphabets? Well, this is easier. The meet of two alphabets, which are sets, is just the set intersection. By these rules, it is easy to give typing rules for operations over automata, for example. And by this way, we can support heterogeneous operations over automata, which is very useful in practice. So, if we have two automata of different types, we can define the type of their union, and the union we have as label set the join of the two label sets, and as weight set the join of the two weight sets. Let's give an example. So let A1 be have label set ABC and weight set Q, and let A2 have label set ABD and weight set some radix. So the rule says that the label set of the result will be the join of the two label sets. So here we have to compute a union, and the result will be ABCD. And for the weight set, we have to compute the join of Q and the radix type, giving a radix type with a different internal weight. Okay? In some cases, we are more lucky and we are able to give a stricter type rule, and this is the case of the synchronized product over automata. Because of the semantics of the operation, we know that the only labels which will belong to the synchronized product will be the labels which are both in the first automaton and in the second automaton. So we don't use a join here, but we use a meet of the label sets. The weight set is still a join. Let's give another example. And here you can see that the product of A1 and A2 will have labels over AB, because that is the common subset of ABC and ABD. This is intuitive because we are computing the synchronized product, which in the unweighted case would yield this the intersection language. Let's give a practical example. It is still the same operation. This is a synchronized product, and by looking at the labels you can see that the set of the labels of the result is the intersection of the labels in the parameters. So we had both alphabets here. They were A, B, C and A, B, D, and you can notice that C and D do not occur in the result, which is expected. But if you look at weights, for example, in this single case, you can notice that if labels have become simpler, weights have become more complicated, which is expected. Can we use this in practice? I will now show you a very quick demo of Vaucanson. In order to use it, I have to first start the server. I have already started it, and then connect to my own machine with a web browser. Then I can open a Python notebook. In this case, just to be faster, I have already prepared one. And here in these cells, I can type Python commands which are evaluated interactively, and the result will be shown. So here I just open the module, then I will create a context. This first context, C1, is just a context with a label set, which is a trivial letter set of A, B, and C, and the associated weight set is Q, the set of rationals. The second context, we still have letters from A to D as labels, but the weight set would be a rational expression internally holding a label set, which is an alphabet from X to Z, and a trivial B set as a weight set. So I will evaluate this by typing Shift and Enter. It works, no result. I will just insert a cell here to show you, that you can show the result. So what is C1 after having it defined? C1 is this context, and notice that we are using that as a value. C2 is slightly more interesting and nicer to see. Okay, so we generate actually MathJax code which is rendered. Now let us define A1 over the first context. So we first generate radexp, and then we obtain an automaton from it, and then we print it. You can see that this semicolon A1 serves to print the result, and this is the corresponding automaton. Let's do the same for an automaton over a second context. This is the result, and now we can try and compute the synchronized product over them, and this is the result. The union is what you can expect. Okay, the union here has two initial states and two final states, which is again expected. It is not a sum. We also have a sum operation which is slightly different, and it computes what we call a standard automaton. This will have a single initial state. You may wonder why the system is I have to first convert the first one to a standard form, and let's do it for the second as well. You may wonder why it took a while to respond the first time. Well, the system employs dynamic compilation of C++ code, so there is a delay the first time we encounter some operation over two specific contexts if it was not used before. You can see that if I recompute the same thing, it will be instantaneous now. Okay, because of course it caches generated code. So we use a sort of C++ compiler as a JIT system. I will go back to the slides. We support type objects, as you saw, as types in the system, and in particular we have this dynamic layer, which is then wrapped by the Python layer, which permits us to not worry about template parameters. And of course, whenever we invoke some computation over automata, we have to dispatch over types and invoke the correct instantiation of C++ templates. This is made automatic by our infrastructure, but it is not trivial by itself. The dispatching routine computes the resulting types, and uses that to call some function pointer. Types can be used to generate code at runtime. This was accurate at the time when the article was written. Now we could say that types are used to generate code at runtime. This already works very nicely. By this system, we can type operations over automata or over radexps. In this case, we have the product and sum of rational expressions, and of course by product of rational expressions we mean their concatenation. And notice again that we support heterogeneous operations, so we can concatenate or sum rational expressions over different contexts, and we are able to obtain a rational expression with a more general type by taking the join of the weight set and the label set in a perfectly natural way. Using the same style, we can give rules for external multiplication by weight on the left and on the right, and we can do the same things over automata by using times, which is the synchronized product, or plus over automata, and by using even more funky operators such as the infiltration product over automata. And again, the external products for by a weight and automaton, by a weight and an automaton, or an automaton and a weight. So what is the current state of the implementation? We support acceptors and transducers in a very satisfactory way. We have a very efficient static API and a flexible dynamic API on top of it with automatic runtime compilation. We have a IPython interface on top of it, which is very friendly to users and students, or even to researchers who just want to do experimentation with the theory without writing complicated C++ programs. We plan in the future to have better transducer support, to have better type checking errors, richer expressions, and metadata on states. This is actually now implemented. What you saw in the demo as the state names of the product, which are pairs here, corresponds to having decorations, by which we mean metadata attached to state names. So this also works very satisfactorily now. I wish to thank all the contributors to the Vaucanson project: Jacques Sakarovich, Sylvain Lombardi, of course Akin Demay, Alexandre Durey-Lutz, myself, Valentin Tolmer, Antoine Petry, Can Lu, Alfred Schmidt, Guillaume Sanchez, Victor Marie Santet, David Moreira. Thank you.